Hello, we are Team 3 from the Intelligent Robotics course from KAIST, and we're going to be making a project proposal with the name of Robotic Theory of Mind and Implicit Collaboration using Epistemic Planning. The members of the group are Omer Tariq, Uzal Kasrakman, and Patrick Vidal.
Our chosen paper title is Implementing Theory of Mind on a Robot Using Dynamic Epistemic Logic. So the authors are Lacy Dissing and Thomas Bolander. So this paper was published on the Conference on Artificial Intelligence 2020. So let me briefly introduce theory of mind. Theory of mind is a reasoning about other agents or robots and their worldviews. Having a theory of mind means having the ability to understand and reason about the mental state of other agents or beliefs. So false belief tasks such as Sally and Annie task domain shown in this slide, used for testing the strength of a theory of mind. The task contains of two human participants, namely Sally and Annie, standing behind a table with three objects, which can be put into three different containers. There can be multiple objects in a container, and the content is not visible without lifting the lid. The human participants, Sally and Annie, can interact with the environment by moving objects in and out of containers, and by entering or leaving the room. So the robot keeps track of all interactions with the environment. In the experiment, Sally puts an object in the first container and leaves. After Sally leaves, Anna takes same object from the first container and puts into the second container. So by doing so, the robot ends up with a false belief. The robot is then asked a series of questions revealing whether the robot has correctly modeled the belief of the participants.
The motivation behind the research is human-robot collaboration. An agent, either human or artificial, trying to achieve its goal in the world must often reason about the actions that should be taken and the order they should be performed. This process is called planning, and humans are pretty good at some types of planning tasks, for example, making a trip and making a meal. Automated planning research attempts to understand this process computationally and build tools for solving this problem. Epistemic planning traditionally involves reasoning about agent knowledge or beliefs. This is a hard computational problem, especially in real-world domains. I will discuss some related work regarding the theory of mind and epistemic planning for human-robot collaboration. Brazil et al. Developed a physical robot solving first-order tasks using a simulation theoretic approach. The robot maintains a distinct belief base for every agent in its environment, representing the first-order beliefs of that agent. The robot filters all percepts such that an agent belief base is only updated if the robot believes that percept was visible to the agent. Melis et al. Use a spatio-temporal belief base to maintain a complex 3D model of the world, allowing the represent the visual perspective of different agents. Similarly to Brazil et al., they can solve a first-order false belief task by maintaining a distinct belief base for each agent. All of these prior works are based upon a simulation theoretic approach, whether the beliefs of other agents are tracked by maintaining a distinct representation simulating the agent's view. Our system differs by supporting higher order belief attribution to unbounded depth, one of the main attractions of model based on epistemic logic and dynamic epistemic logic engine. Sandra Devine presented a system that allows to estimate and maintain mental states of other agents concerning not only the environment, but also about the state of goals, plans, and actions in the context of human-robot shared plan execution. In this study, the estimated mental states concern not only observable information about the environment, but also the state of current and previous goals, plans, and actions, and these mental states are then taken into account during the execution of a shared plan in order to reduce unnecessary communication to produce a less intrusive behavior of the robot. In general, epistemic planning considers the following problem. Given any current state of knowledge and a desirable state of knowledge. How do I get from one to another? It is of central importance in settings where agents need to able to reason about their own lack of knowledge. For example, to make plans of how to achieve the required knowledge. It is also essential in multi-agent planning where successful coordination and collaboration can only be expected if agents are able to reason about the knowledge, uncertainty, and capabilities of other agents.
For the current implementation done in the paper, it was implemented using a Pepper robot in order to manipulate the environment and to perceive and speak with humans. The perception layer was taking the skeleton detection of the humans, the tag detector for the boxes and the cubes, and then a face recognition in order to detect when was Sally or Annie inside the room. Last, the authors implemented a dynamic epistemic engine that is the engine that tracks the belief from all the other agents. When all these three are combined, they are able to pass a Sally-Annie test and the robot can recognize when one of the human agents has a false belief state. The given paper didn't have any implementation supported, but the same author have published later on a benchmarking repository and a benchmark paper regards the dynamic epistemic logic. This code doesn't have any interaction with any robotic environment or with any perception. There is no simulation or robot integration, and the same way there's no perception that is been described in the previous paper. So for our paper replication approach, we're gonna simulate the Pepper robot and the perception of the environment. This is gonna be done either using ROS or Unity. And then the dynamic epistemic engine can be scrapped from the authors, from the other papers that they have done, or from any other engine that is probably available in the internet. One of the issues of using other engines is like they might be coupled with some other implementation. And that is, for example, the case of the paper that was used to benchmark different approach for the epistemic logic that is really coupled to benchmarking, and it's really hard to implement it with a robotic system. Once all those three are in place, we can simulate the Sally-Annie test in a simulated environment, either in ROS or Unity. And then by the movement of different agents and by losing the vision with the agents and modifying the environment, the robot should be able to identify if either Annie or Sally has a bold belief of the state. In that case, will mean that the robot can identify that Sally is trying to search for a box, for a cube in a box, and that box doesn't contain the cube. In that sense, the robot then will notify the human that the box contains the wrong cube. For the improvements, we want to focus on human-robot collaboration, and one of the active research is when should the robot collaborate or when should the robot try to help another agent. In this way, we want to implement an implicit collaboration, and that can be done since the robot right now keep tracks of another human and other agents' belief states. So, for example, if we have the example where a robot knows that the human is leaving the room, the robot knows that the human doesn't have the keys to leave the room, and the robot knows that the door is closed, then the robot should immediately either open the door for the other agent or should hand me the keys for the other agents. This automated planning can be implemented using automated planning or PDDL, planning domain definition language, and also using epistemic logic. This has been called epistemic planning and an extension of automated planning. The major idea of using epistemic planning is using other agents' belief states as preconditions in each of the actions. In this case, if the robot detects a precondition where the agents want to leave the room and the agent doesn't have the keys and the door is closed, then that should immediately activate an action for the robot to help the other agents. For current proposals for current proposals of testing the implementation, we are trying to find a collaboration with a human robot, and we will be implementing epistemic planning on top of the previous implementation from the authors. Thank you for listening.